My presentation on smart farming with the power of robotics for the Vodafone competition Think Big, then Think Bigger. Agriculture is one of the biggest fields in the UK, taking up 70% of the country's land area, employing 1.5% of the total workforce, and contributing £10 billion to the total gross value. However, since the year 2020, by looking at the research done by the Department for Environment, Food and Rural Affairs, the agricultural area has decreased by 1.5%. This resulted in a wheat decrease by 40%, winter barley down by 46%, and this trend continued with the oats yield decreasing by 17% per hectare. The oilseed harvest was the one that was hit the hardest, with a harvest decrease by 41% and a planted area decrease of 28%. And these changes can be seen countrywide in different sectors of agriculture. Now, this issue can be attributed to the pandemic, as well as the change in jobs and the shift from manual labor to more mechanical and automated systems. So this is where Vodafone can step in. What they can do is, based on the Vodafone's purpose pillars, they can connect people and things and digitalize critical sectors while also using sustainable methods and systems that do not increase the carbon footprint. So by combining Vodafone's experience and technology in terms of networking infrastructure with robotics, artificial intelligence, and the Internet of Things, we can revitalize the farm sector. In terms of robotics, with the use of robotics and more specifically ROS, which is a middleware operating system for robots, we can create a web of interconnected devices with examples ranging from drones patrolling an area and going to specific waypoints and vehicles performing automated tasks. And thanks to computer vision, we can enable these devices to derive useful information from visual inputs. And when combined with artificial intelligence, we can identify specific scenarios and react to events. With machine learning, systems can use previous historical data in order to accurately predict what will happen in the future. And all of these devices and systems, they need to be connected and communicate with each other. So thanks to Internet of Things, they can connect and exchange data over the internet or with other communication networks. Firstly, robotics is a big field and it spans different sectors. And we can use some of these sectors in order to improve farm as we know it. Sensors can be used to locally monitor soil, moisture level, temperature and humidity, UV index, and much more. And with ROS, we can have multiple drones that can move to specific waypoints at given times, monitoring the crops, checking for wild plants, and sending out vital information. The same way, we can have harvesting systems that can be automatically activated to autonomously navigate to and from the crop's location. Now, having a fully autonomous farm, thanks to all of these different devices, would enable the optimization of crop harvesting per patch while identifying the best procedure to take in case of events. So rather than processing the whole wide land for farming, we can divide it into quadrants, and then we can only process very specific particular things with different devices. So I have performed some research myself in order to further develop this idea. So I've used two modules called Nikla Sense ME and Arduino Nano 30 BLE Sense, which provide a huge array of sensors, but the sensors that I'm more interested in are the pressure, temperature, and humidity. So thanks to these two boards combined, I can do temperature, humidity, and pressure sensor fusion so that my values are more accurate. And once these values have been calibrated, I can then use physics formulas in order to increase the amount of information that I can have. So I can derive the altitude, the sea level pressure, the dew point, the relative humidity, and even more specific information such as the cloud-based altitude or cloud-based temperature, so that in case a plane needs to drop pesticides, they can use this information in order to only perform the activity on specific days. Now, by taking this information and passing it to machine learning, we can actually identify and classify the conditions of the environment to 5 different weather types: fair, rain, cloudy, overcast, or snow. So there are many different algorithms, and the way they work is machine learning does not require explicit programming like traditional programming. It does not require instructions. It learns from the patterns and the details that it finds in the data that it has been provided with. So by doing that, and by using different algorithms for machine learning, I have taken 20 years from the year 2000 to the year 2019 of weather data from the Heathrow weather station, and I've given to the machine learning algorithm temperature, humidity, pressure, feels-like temperature, dew point, and UV index. And by performing all the additional tasks in optimizing the algorithm itself, I found out that the best algorithm would be an XGBoost classifier, which once optimized for the data itself, it is able to reach 89% accuracy in rain, 73% accuracy for fair, 100% for snow, 3.8% for cloudy, and 2.5 for overcast. Now, I myself, as the programmer, have chosen to dedicate my attention to snow, rain, and fair. However, farmers and owners of farms can actually choose to dedicate themselves and calibrate these machine learning algorithms to specific events. So if they're more interested in knowing whether or not it will be cloudy in a specific day, then we can create a machine learning model that has 100% accuracy on detecting whether or not it's cloudy and lower accuracy on every other class. But the machine learning doesn't stop here. I can move from a classification problem to a regression problem. I can use the same historical data as said before with same algorithms in order to predict the amount of rainfall in millimeters before it happens. And this can happen with high accuracy and fully offline. So here I've taken the decision tree regressor and I have trained it on the 20 years. And then I have used 2 years from 2020 to 2021 in order to compare the values that I already know because these events have happened to the prediction of my machine learning model. So here in black, I have the actual accurate values, and in white, I have the predicted values. And we can see that it is fairly accurate. And in fact, it is able to be accurate within an R-squared error of only 10% and a mean absolute deviation error of only 9% over 2 full years. And that's amazing for a machine learning algorithm. Now, since I was talking about machine learning, it would be interesting to use some other type of software combined with machine learning in order to understand if plants have diseases or not. And what we can do is we can use computer vision with fixed cameras in greenhouses or drones with attached cameras in the case of large fields in order to extract a lot of visual information and identify whether or not these plants have any diseases or if they're healthy. So here, for example, I'm showing how with the use of computer vision, I can extract the information in regards to the amount of leaves, the amount of diameters per leaf, the actual dimension of the total plant, the shade of the color, and this can tell me whether or not the plant is healthy. Moreover, I can use a different machine learning and computer vision algorithm in order to check if my crops is in the presence of wild plants, which can interfere with the actual harvest itself. So what I can do is if I have a drone passing over the field and the drone itself identifies that there are wild plants around my crops, I can then activate a separate machine that can go and remove these wild plants. Moreover, if I combined computer vision with artificial intelligence in the form of deep learning, I can then identify if my crops require specific instructions like irrigation, or maybe if I need to just harvest them because they are ready. So in the case of these tomatoes here on the left side, the red tomatoes, I can take the shade of the color red, how bright it is, as an information. I can take the diameter of it, I can take the shape of it, and then I can say if I have this many within a certain range, so I can have a cluster of them, then send over a device to collect them. And then for the green tomatoes on the right side, maybe I can activate an irrigation system in order to have them be prime readier. So I can use this type of a system with autonomous pesticides, for example. So I can have a drone that's patrolling over, sends the information, and then have a separate drone that comes and deploys the pesticide, which will also lower the pollution and fruit contamination of the pesticides, because again, this only happens in specific sectors of this whole wide area. And I can also have autonomous harvesting. I can have different machines sent to different locations, being able to harvest differently. And once these machines have harvested everything, they can send a signal out for another machine to come remove the plant and plant new seeds. This will increase the actual production value, because what that does is you can continuously plant and can continuously harvest, and you can increase the efficiency of the land itself. Now, all of these devices that I've talked about, they have to be interconnected. So thanks to the Internet of Things, we can have these systems communicate with each other. So the way we can do that is we can have beacons placed around the wide area, such as the one shown in the slide here. And then we can have all the little sensors, such as the soil moisture or the temperature sensors, send low-range information in the form of Bluetooth or Wi-Fi to this beacon. And then this beacon can use Vodafone's leading 5G networking technology to send that over to a server. Then at the server itself, we can actually create a digital twin. Now, what a digital twin is, it informs us where every single device is at every single moment of time. And it can also tell us about everything that is around it and the actual level of performance of the device itself. And all of this information can then be provided to the users, so to the owner of the farm, for example, through specialized bespoke visualization data systems, or with visualization software that's already on the market in the form of Tableau. And this gives the ability of the data to be used, analyzed, and controlled at any given time, anywhere on the globe, giving never before seen granularity in control. Now, all of these systems have challenges in implementing them. First of all the devices must be connected to the main hub and server at all times. Any power outage and network failure would stop the process. Now, thanks to Vodafone's technology and experience in this field, this should be no problem. Moreover, in order to identify specific fruits or specific diseases, we need to create custom datasets for the computer vision software and artificial intelligence. So this can take some time, and this is specifically per farm and per plant. So it cannot be widely used everywhere. And this connects with the next challenge of being able to mass produce the devices and the software, but then there will be the need of sending out an engineer that will have to tweak the little details in order to ensure that the devices perform at the highest performance. Last but not least, all these challenges and all these systems in such a big ecosystem needs to be implemented in a perfect way, and this can take a long time. So the actual time frame should be taken into consideration when trying to deploy such a wide-scale system. And lastly, technology is amazing until it stops working, and continuous maintenance is required to keep the gears turning in such a complex system. With all this said, I'd like to remind you that the main takeaway of this presentation is the word interconnected. Thank you for the attention provided. And if you have any questions, please feel free to ask anything.